Can you hear me? Thank you. So, 1.3 billion years ago, when multicellular life was just spreading over the Earth, but in a galaxy far, far away, two black holes circled around and around each other. This is what they would have looked like to you had you been there looking with your own eyes. You see the black disks, which are the shadows of the black holes against a distant star field. And then you see the swirling of the stellar images caused by gravitational lensing, the deflection of the starlight by the black hole. Black holes filed around, collided, and merged, and produced a gigantic burst of gravitational waves, ripples in the fabric of space and time that traveled outward, out from the galaxy in which the black holes lived, into interstellar space, across the great reaches of interstellar space, and arrived at the outer reaches of our own Milky Way galaxy 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. For 50,000 years, they traveled onward into our galaxy and reached the Earth on the 14th of September, 2015. They arrived at the Earth near the Antarctic Peninsula, near the South Pole. They traveled upward through the Earth. They reached the LIGO gravitational wave detector, the laser interferometer gravitational wave detector in Livingston, Louisiana, near New Orleans. And 7 milliseconds later, they reached and passed through our detector in Hanford, Washington. The LIGO scientific collaboration, consisting of 1,000 members in 16 nations at 80 different universities and institutes. The members of the collaboration looked in great detail at the signal and at the behavior of the gravitational wave detector at the time the signal came in. It took 5 months to be absolutely sure that what we were seeing were gravitational waves. And when we were sure, we announced the result on February 11 of 2016, an announcement that caught the imagination of people around the world and made headlines in all the major newspapers around the world, such as the New York Times and the Times of India. So how did we get here? How did that great discovery of approximately 1 year ago happen? Well, of course, it began with Albert Einstein. In 1916, 100 years ago, he predicted the existence of gravitational waves. And he told us that the gravitational waves are ripples in the fabric of space and time, that as they pass through us, they will stretch and squeeze space, as shown here. So that the farther apart two pieces of space are, the more they will be moved apart. We call this a strain, a gravitational wave strain. And more specifically, the inertial frames separated from each other because they ride on space. They move back and forth with respect to each other in the manner so described. Einstein, in his seminal paper, said, in essence, that these gravitational waves are so weak that humans would probably never, ever be able to see them. Einstein was wrong. It was Joseph Weber at the University of Maryland in the 1960s who first had the courage to build a gravitational wave detector and begin to develop the technology for searching for gravitational waves. He did not succeed, but these were the seeds on which LIGO was based. Now, I arrived at Caltech as a young professor in 1967, and I was very much influenced by Joe Weber. I had gone hiking with him in the French Alps. We had talked for many, many hours about his experiment. And so I set up a theory group to work on the theory of gravitational waves and sources of gravitational waves, especially black holes and neutron stars. In parallel, Ray Weiss, who had been with me when I was a graduate student at Princeton, we'd been together, he moved into a professorship at the Massachusetts Institute of Technology, MIT, and he began to think about techniques for detecting gravitational waves and became the primary inventor of the technique that we use in LIGO, the technique shown here. And the basic idea of this gravitational wave detector, this is not, I won't use that. The basic idea of the gravitational wave detector is that you hang four masses from overhead supports along two arms that are perpendicular to each other. Let's see if that, yeah, I think that's not any better. That's all right. I'll get by without. Yeah, that's okay. So you hang four masses from overhead supports, and when the gravitational wave comes by, it moves these masses together while it's moving those masses apart. Then it moves these together while it's moving these apart. And that pattern of stretching and squeezing of the separation between these masses is monitored using a technique called laser interferometry with laser beams. And so you're monitoring, measuring the changes in the difference between the arm lengths of those two arms of the interferometer. And the predictions that I was making and my colleagues were making on the basis of the theory of black holes and neutron stars said that in order to succeed, Ray Weiss would have to achieve a strain, a fractional change in the separation of those mirrors at a level of 1 part in 10 to the 21. Now that's very, very small. But he then went on to argue that this would be possible technologically. And he described all of the major noise sources that these gravitational wave detectors would have to face. And he described how you might deal with them. And he then computed what the resulting sensitivity might be and concluded that 10 to the minus 21 was possible but would be very, very difficult. Just how big is 10 to the minus 21? Well, it corresponds to the following. If you take 1 centimeter, you divide it by a factor of 100, you get the thickness of a human hair. Divide by 100 again, you get the wavelength of light, the light that is used to make these measurements. You divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 100, and you get the strength of the motions, the magnitude of the motions of those mirrors that we would have to measure. And that, in fact, was the magnitude of the motions of the mirrors that we did measure in our first discovery of gravitational waves. That's phenomenally small, extremely difficult. And so, but by 1976, after initial skepticism, I became convinced that this experiment, this kind of a gravitational wave detector might in fact succeed, but a huge R&D effort would lie ahead that would be required to develop measurement technology far beyond anything anyone had previously conceived. But this was very important to do, it seemed to me, because when I compared the electromagnetic waves that astronomers normally use to study the universe with gravitational waves, the contrasts were really quite startling. Electromagnetic waves are oscillations of the electromagnetic field that propagate through space-time, while gravitational waves are oscillations in the very fabric of space-time itself. The electromagnetic waves are normally an incoherent superposition of emission from individual particles and atoms and molecules, whereas the gravitational waves are coherent emission by the bulk motion of matter, or the bulk motion of energy in some other form, such as the warped space-time of black holes. Electromagnetic waves are all too easily absorbed and scattered in traveling from their source to the Earth, whereas gravitational waves are never significantly absorbed or scattered, not even very near the Big Bang. Gravitational waves could come off the Big Bang and travel unscathed to us and bring us an image of how the universe was born. And so the implications were that many gravitational wave sources won't be seen electromagnetically. We can explore things that could never be explored in any other way. Great surprises are likely, and we could have a revolution in our understanding of the universe if we could succeed in detecting these waves. And so, convinced that it might be possible, I then argued with my colleagues at Caltech, the faculty and the administration, that we should go forward and build an experimental effort at Caltech to complement the effort that Ray Weiss was leading at MIT. Caltech embraced this enthusiastically. We brought Ronald Drever from Glasgow, Scotland, and Stan Whitcomb from the University of Chicago to lead the effort. And they led the construction of a 40-meter prototype gravity wave detector of the type Weiss had invented. And Ron Drever invented some major improvements on Weiss's design, which made it work even better than Weiss had imagined it would work. In that same period as we were building this detector at Caltech, this prototype, Weiss at MIT and his group were continuing work on their prototype, but more importantly, Weiss led the feasibility study for kilometer-scale interferometers. We knew we would have to build interferometers that had kilometer-scale arms, and he led a study that showed that this was feasible and financially possible. So the result was that in 1984, MIT and Caltech made a pact, a memorandum of understanding, with the blessing of the United States National Science Foundation, which led to the creation of LIGO, the Laser Interferometer Gravitational Wave Observatory project. We continued to work on the R&D to underpin these detectors, work on the prototypes, and in 1989 we were ready to propose the construction of LIGO. We proposed in 1989 to the National Science Foundation that we would build facilities to house these interferometers, and then we would build the interferometers in 2 stages. We would build an initial set of interferometers at a sensitivity where you would have to be lucky to see any gravitational waves, and then advanced interferometers at sensitivity where we should see lots of waves. We had to do it in 2 steps in order to have a high probability of success. The technological distance from the prototypes to the final interferometers was just too great to do it in 1 step. And so we were funded in 1992 with the understanding we would do it in 2 steps. The U.S. Congress has backed us firmly ever since and has invested $1.1 billion of U.S. taxpayer money in this project. Now, it was much too difficult and much too complex for MIT and Caltech to do this project alone. Fortunately, in a number of different locations around the world, there were scientists who were working on the development of the technology and the understanding of the sources and the data analysis techniques. For example, in India, beginning in 1990, right after we had submitted our proposal, the entire community around the world knew we were moving forward, or we were hoping to move forward, and enthusiasm built. And here in India, at the Raman Research Institute in Bangalore, Bala Iyer's group began work on the computation of the shapes of the waves, the gravitational waveforms that we would detect, shapes we absolutely had to know in order to be able to find the waves and figure out what they meant. At IUCAA in Pune, Sanjeev Dhurandar's group began intensive work on developing data analysis techniques for LIGO. These, then, efforts were incorporated along with efforts from a number of other groups around the world into a single organization called the LIGO Scientific Collaboration, the LSC, which now has 1,000 scientists and engineers in 80 institutions in 16 nations, with India playing a major role. The LSC was the brainchild, the invention of our LIGO director, Barry Barish, who was the person who led us in moving from small-scale prototypes into the modern era with large gravitational wave detectors and a 1,000-person project. That kind of leadership is absolutely essential in order to have success. From 1994 to 1999, we built the facilities. 2000 to 2010, we built and operated the initial interferometers. From 2010 to 2015, under a new director, David Reitze, we installed the advanced interferometers. And then on September 14, 2015, when we were just preparing for our first search, but had not yet made it official that we were searching, the first signal arrived. And it was fantastic. It was so strong that I couldn't believe it was real. None of us could believe it was real. It's so strong and so clean. But as I said, after about 5 months of intense study, it became absolutely clear that this was the real thing. This is what the signal looked like in the detector at Livingston, Louisiana. This is the oscillating stretch and squeeze as a function of time. And the signal was far stronger than we expected. It was so strong that there's been no signal processing put onto this except for removing the detector output above 350 hertz frequency, removing it below 35 hertz because we're quite noisy outside of that band. But over this factor of 10 frequency band from 35 to 350 hertz, this is the raw signal. There is the raw signal in Hanford, Washington. Here is the signal cleaned up and compared with numerical relativity simulations of 2 colliding black holes. And that comparison is so perfect that it tells us with complete confidence that these were two black holes, 1.3 billion light years from Earth, that one of them weighed 29 solar masses, the other weighed 36 solar masses, a combination of 65 solar masses, and the final black hole was smaller. It was 62 solar masses. 3 solar masses came off as gravitational waves. It is as though you had taken 3 suns and annihilated them and turned all of their mass into gravitational wave energy. And it was done so quickly, in a fraction of a second, that the total power output, the energy per unit time during the collision, was 50 times larger than the total luminosity in light of all the stars in the universe put together. 50 universe luminosity in this very brief collision that put out the gravitational waves. Just absolutely amazing. We saw 2 more gravitational waves during our first search for gravitational waves, which lasted from September to January. And the second one, we're not 100% sure it was real, but we are almost sure. It was 23 solar mass and a 13 solar mass black holes merging much farther away, 3 billion light years from Earth, a third of the way to the edge of the observable universe. And it produced 1.5 solar masses of gravitational wave energy. The third one, 14 solar masses and 8 solar masses, 1.4 billion light years from Earth, and 1 solar mass in gravitational wave energy. And so we are off and running in the exploration of the universe with gravitational wave. Having identified the nature of a source by comparing the theoretical waveforms with the observed waveforms, we could then go back to numerical relativity simulations for the parameter values that we had measured, the 2 initial masses of the black holes and spins. We also get some information about how fast they are spinning. Go back to the computer simulations to deduce what the black holes were doing during the merger. Now, black holes are not made from matter like you and I. They are made from warped space and time. And so this diagram depicts that warpage. The shape of this surface, it looks like the horn of a trumpet, is the shape of space around the black hole. If I take an equatorial slice through a single black hole, a fast-spinning black hole, an equatorial slice, and then I look at it in a flat, higher dimensional space. We call it an embedding space, and then moving interstellar, it's called the bulk. And physicists often call it the bulk, the 5th dimension. It has to bend down like that in order to fit into the higher dimensional space. So that's the shape of space. The color coding shows the slowing of time. Where it's yellow, time is flowing at 10% the rate that it is back here on Earth. And the black location down to the bottom is the black hole's horizon, which appears here to be a circle. That's because I've removed 1 dimension. I only have the dimension of the slice, equatorial slice through the black hole. If I restore that other dimension, what is shown as a circle here becomes a spheroid, a flattened sphere, black hole horizon. Now, I also am showing little arrows that show the dragging of space into motion, so-called dragging of inertial frames by the spin of the black hole, or the motions of the black holes, as in this case. So here now is a similar diagram showing what that initial discovered black hole pair, we call it GW150914, what it would have looked like if you had looked in from a higher dimension and watched the black holes collide. So each black hole is that trumpet-shaped horn. The color coding is the slowing of time. The arrows are dragging of space into motion. And this has gone into slow motion. The actual lapse of time is up at the top. And it is as though you had created a short but gigantic storm in the fabric of space and time. And then it oscillates and the gravitational waves travel away. The gigantic distortion of space was from the black holes colliding. And these computer simulations teach us much more than that. That gives you a first glimpse of what we are learning about black holes through this combination of the simulations and the observation. Now, LIGO today is rather like Galileo in 1609. In 1609, he turned a telescope on the sky for the first time and discovered the 4 moons of Jupiter. LIGO has turned a gravitational wave detector onto the sky and discovered 3 colliding pairs of black holes. And just as Galileo's discoveries have matured into a very rich modern optical astronomy, so similarly, LIGO's beginning that we now have in our hands will mature into a rich and diverse gravitational astronomy. The first step in moving in that direction is to bring the advanced LIGO detectors that are now operating to design sensitivity. They're only at 1/3 their design sensitivity. They have noise that's 3 times larger in terms of the stretch and squeeze than their design. And this is being done currently through a series of steps where we search for gravitational waves for several months, from September of 2015 to January of 2016. Then we improve the detectors for half or 3/4 of a year, and then we search again. And our second search began about a month ago, began on November 30th. In the first search, the rate of binary black hole mergers, black hole collisions, was about 1 per month. We saw 3 in a search period of about 4 months. When we reach design sensitivity, we'll be able to see 3 times farther. This is 2019, 2020. See 3 times farther into the universe. We'll see a volume of the universe that's 3 cubed larger, 27 times greater than we now cover. And that means that the binary black hole mergers rate should go up by a factor of 27. So that would become about 1 per day. However, I should caution you that this is based on small numbers. When you deal with numbers like 3 that have been discovered so far, and 1 you're not absolutely sure of, the uncertainties in predictions for the future are a little bigger than a factor of 10. But still, we're off and running, and the rate is going to go up very rapidly. But binary black hole collisions are not our only source. We expect to see a number of other things. We will see spinning neutron stars, pulsars, that have little mountains on their surfaces or deformations from axial symmetry that emit continuous gravitational waves oscillating on and on and on and on, carrying information about the properties of the stars. We will watch black holes tear apart companion neutron stars. We will watch 2 neutron stars orbiting each other collide and merge. We will explore the cores of supernova explosions, and we will almost certainly have some huge surprises. Every time humanity has opened a new window onto the universe, a new way of observing the universe, there have been big surprises. And this is such a radically new way that the surprises are almost certainly going to be even bigger than we have ever seen before. And most of these sources, all of them that I've talked about so far, except for the colliding black holes, involve matter, and matter radiates electromagnetic waves. And so we are entering into an era of multi-messenger astronomy where you study sources such as colliding neutron stars or supernova explosions with gravitational waves plus X-rays and gamma rays and light and radio waves and other frequency bands electromagnetically. But there's a big problem with this, and that is we need to be able to tell, as gravitational astronomers, we need to be able to tell our electromagnetic colleagues where to look on the sky. And we have lousy, very, very bad angular resolution. You see here the uncertainty in where on the sky, a point on the sky is represented by the location on Earth that is directly below it. So for our first gravitational wave discovery down there near the South Pole, you see the direction in which the waves came, but it's a great big banana-shaped uncertainty error box. The other 2 of the error boxes are even bigger, and there are 2 sets of error boxes. And so we really don't know at all well where the gravitational waves are coming from. The reason is that our method of determining the direction of the source is by the time delay in the arrival of the signal at different locations on the Earth. And so we need additional detectors at other locations. There is something called the Virgo gravitational wave detector that will go online and participate in our search in this year, in 2017. There is a detector called LIGO India that we are planning as a collaboration between the US and India to install and be operating in the early 2020s. And then there is a detector called Kagra in Japan that should go into operation around 2019, 2020. And so with those, there will be huge improvements. As soon as we have Virgo operating as well, this is what our error boxes on the sky will look like. they are still very long in one direction, but they are much narrowed down in another direction. When we bring in LIGO India, the error boxes become truly respectable, and that's why India is so crucial, so we can tell the electromagnetic astronomers where they should look in order to see this. The Japanese Kagura detector will improve things in the east-west direction, but we're already very good in the east-west direction. The crucial thing is the north-south direction. That comes from LIGO India. So on March 31st, 2016, the Secretary of the Department of Atomic Energy of India and the Director of the U.S. National Science Foundation signed a Memorandum of Understanding for LIGO India in the presence of the Prime Minister Modi of India, but in Washington, D.C. Under this agreement, the Indian government and the Indian scientists commit to construct and operate for 10 years an advanced LIGO observatory interferometer on Indian soil. The U.S. commits to provide the detector components, which we already have. They're sitting in boxes, just waiting to be moved to India. The facility designs and the software. And we commit to close technology collaboration with the Indian scientists on photonics, lasers, control systems, vacuum systems, and so forth. And this also entails making improvements in LIGO India that go beyond our current advanced LIGO detectors. Because by the early 2020s, when LIGO India goes online, we expect to have improved our LIGO detectors a modest amount, so we can see 1.6 times farther. We'll see black hole collisions at a rate of a few per day. By the late 2020s, we will have a third generation detectors, according to our plan, which will see 2 times farther than this advanced LIGO Plus, A+. Black hole collisions at 1 an hour. And in the 2030s, we hope to have operating by late 2030s a 4th generation called Cosmic Explorer, with arm lengths 10 times longer than the current LIGO detectors, seeing 5 times further still, capable of seeing every black hole collision that occurs in our universe with masses less than about 1,000 solar masses. Doing this, these improvements, involve some really remarkable new technology. In advanced LIGO, in order to succeed with advanced LIGO in 2019-2020, we will be monitoring the motion of those 40-kilogram mirrors, the ends of these laser beams. Monitor that motion to a precision that is at half of the width of the Schrodinger wave function of the center of degree, the center of mass degree of freedom of the mirrors. What that means is that these mirrors will be behaving quantum mechanically. We monitor just 1 degree of freedom of the mirrors, the center of mass motion, and we will be seeing quantum fluctuations in the position of those mirrors. Kinds of fluctuations that have only been seen in the past with molecules and atoms and are beginning to be seen with nanoscale structures. But we will see them with 40 kilogram mirrors. And in the 3rd and 4th generation, we will be making measurements at 1/6 the width of the wave function, well below, quite far below the quantum fluctuation of the position of the mirrors. In order to do this, then, in order to deal with the fact that the first time humans are seeing human-sized objects behave quantum mechanically, we have developed what is called quantum non-demolition technology. And quantum non-demolition technology I don't have time to go into, but it's marvelous new technology that is a piece of the new field of quantum information technology or quantum information science. Other branches of this new field of technology that you may be familiar with are quantum cryptography and quantum computing. But quantum non-demolition technology is built into advanced LIGO, will be built into LIGO India, and we are bringing thereby by far the most advanced measurement technology that humans have ever developed into India as part of this collaboration. Now, even more remarkable, over the next 15 years, we expect to open 4 gravitational wave windows onto the universe, the analogs of X-ray astronomy, radio astronomy, optical astronomy, infrared astronomy. That is 4 different frequency bands in gravitational wave observation. We have already opened the first of these. LIGO looks at gravitational waves that have periods of oscillation. It's simpler for me to talk about periods than frequencies. Periods of oscillations of milliseconds. LISA, an analog of LIGO involving 3 spacecraft that track each other with laser beams, that will be launched, we expect, by the European Space Agency, perhaps with some US participation in 2030. It will look at gravitational waves with periods of minutes to hours. Something called pulsar timing arrays using large radio telescopes that look at pulsars on the sky. Each pulsar ticks. It actually is a spinning neutron star with a beam that sweeps past Earth very regularly with a fraction of a second period, typically between pulses that arrive at Earth. You use a radio telescope or a set of radio telescopes to monitor the ticking rate of these pulsars, the period of oscillation of these pulsars, to very high precision. And if a gravitational wave sweeps across the Earth, it speeds up and slows down our clocks. And as a result, the pulsars appear to speed up and slow down synchronously. And that technique, looking for gravitational waves with periods of years to decades, is very near success. Will likely have success around 2020 is my guess, maybe 2025. And then, something I'll talk about at the end, but looking for gravitational waves with periods of billions of years or hundreds of millions of years, similar to the age of the universe, a technique called CMB polarization that will be at the very end of my talk in just a few minutes, should succeed in the period between 2020 and 25. And so by roughly 2030, maybe 2035, we will have 4 different frequency bands using different kinds of detectors in operation doing gravitational astronomy and contributing to our understanding of the universe we live in. By 2030, we will have the major theme in this field, exploring the first 1 second of the life of the universe. And let me explain that this way. As we look out on the sky, we see coming to us from the sky photons called the cosmic microwave background that arose from the very hot matter in the very early universe. Those photons were trapped by the hot matter, the hot gas, up until the universe was roughly 100,000, well, really more like 380,000 years old. And then there was a plasma recombination. Electrons got swallowed up by protons, and suddenly the photons were no longer being scattered by the electrons, and they could propagate freely. And so they brought us an image of images of our universe when the universe was a few 100,000 years old. And there have been marvelous discoveries in cosmology with these photons. If we could look out and see neutrinos, very penetrating fundamental particles, from the Big Bang, we would be able to see them back to an era of 1 second. Earlier than 1 second, the neutrinos were trapped and scattered by electrons and high-energy particles, and they couldn't propagate. The only kind of radiation that can travel freely from the era of the Big Bang to us today is gravitational waves, and so it is our only tool for probing the first 1 second of the life of our universe. And in fact, there was rich violence in that first 1 second of our universe's life, and I'm going to give you 2 examples. And these are examples of what we expect to be able to explore with gravitational wave detectors in the next several decades. The first is what I promised you about the cosmic microwave background polarization. With this, we expect to explore primordial gravitational waves, that is, gravitational waves that were produced in the Big Bang and were amplified by an early period of very rapid inflation of the universe, very rapid expansion of the universe that we are now almost sure happened. And theory tells us that those much amplified waves, amplified by inflation when the universe was something like 10 to the minus 34 seconds old, unbelievably young, that these waves should have interacted with the primordial plasma, the electrons and protons, at the time that the electrons were being swallowed onto the protons, and the plasma was being squeezed and stretched by the gravitational waves, and that interaction should have put onto the photons, which are now the cosmic microwaves, should have put a polarization on that has a particular pattern that corresponds to what would be produced by these primordial gravitational waves. That pattern has been discovered by our colleagues who observed the cosmic microwave background, but they have noise that arises from a similar kind of polarization being produced by dust in interstellar gas. And so the crucial thing is to come to understand that noise, remove it, and then be able to actually see the imprint of the primordial gravitational waves produced in the Big Bang and amplified by inflation. And this will teach us much about inflation, crucial things about inflation, and perhaps things about the Big Bang itself. The second example is the birth of the fundamental forces. When the universe was 1/1,000,000th of a second old, 10 to the minus 12 seconds old, the electromagnetic force and the weak nuclear force came apart. Okay, yes, and I have 2 slides. He's giving me 2 minutes and I have 2 slides. When the universe was 10 to the minus 12 seconds old, the electromagnetic force and the weak nuclear force came apart, gained their individual identities. Before that, they were combined together in something called the electroweak force. Those forces then were separate. The electromagnetic force existed. The electric field and magnetic field existed inside bubbles, we think, which associated with, if this was what is called a first-order phase transition, these bubbles will have expanded at the speed of light, collided, and produced gravitational waves. And those gravitational waves today are in the frequency band for Lisa's observation. And similarly, LIGO could see phased gravitational waves from what is called phase transitions when the universe was 10 to the minus 22 seconds old, but we know nothing about the physics at that very early phase. So in conclusion, gravitational waves will be a major tool for astronomy into the next century and beyond. And I've not given you much in the way of technical details, but if you would like to know them, there will be 3 talks on Friday at this conference, in which Jeeth will talk about the discovery of gravitational waves, a talk by Bala Iyer on advanced LIGO, the discovery instrument, and the future of gravitational wave astronomy, in particular the Indian contribution by Sanjit Mitra. Thank you.